Hello AP Calc BC. We're beginning chapter 10, which is the last chapter in your textbook and in the AP Calculus curriculum. And so this is a little bit of a hodgepodge of all the things that we haven't covered yet, but they are actually all related. We're going to be doing parametrics, polars, and vectors. And each one has a relation to the other. So Topic 1, parametric curves in the plane, and then slope and concavity and arc length. So we did parametrics way back when in chapter 2 when we started the year, just as kind of a review of what you were supposed to do with parametrics in pre-calculus. And now in chapter 10, we'll spend just a little bit reviewing how they work again, and then the calculus applications of them, which of course are going to include derivatives and integrals. Okay. So by the end of this topic, you should be able to sketch parametric curves and convert them to Cartesian format by eliminating the parameter. So hopefully that's just a review of some things that we did in the beginning of the year in chapter 2. Differentiate parametric curves to find the max, min, and inflection points. So that's where the calculus is coming in. We'll be taking the derivatives of them. And then find the arc length of a parametric curve. So in that case, we'll be using our integrals. So a few things. So parametric, vector, and polar functions. So these are the things that we're going to be looking at in chapter 10. So these are some different kinds of curves, and they all tell us that they can all be used to describe motion in a plane that does not move along a straight line. With parametric curves, so we have that third variable thrown in there. So we'll have something as a function for x, a function for y, and then both of those will be in terms of some other variable t or theta. So we can have that extra function to show us how things relate to time or an angle that we're moving through. Vector functions are going to show us the motion of an object with magnitude and direction. Okay, so whether it's velocity or acceleration, and then also the direction that we're going in. And then polar functions, polar functions, those are going to be things those are functions that are used to describe the movement of objects that aren't in a straight line, that are in a curve, and the curves kind of have cycles, and sometimes they don't backtrack on the curve, but they trace another area over again. And so we can use polar functions to show an object that traces a certain area more than once. And so we'll use what we already know about single variable calculus with derivatives and integrals and apply that to these things. And in some cases it works the same way, and in some cases we have to learn something new, learn a new detail about all of this. So first thing we need to talk about is just a quick review of parametric functions from back in chapter 2. Okay, so parametric functions allow us to define some curves that would be very difficult or impossible to find if we only use one function with two variables, x and y. And so what we do with parametric functions is we have a function for y, a function for x. We throw in another variable, which is going to be a parameter, and that parameter we can have t, or t if we're talking about time, or if we want to talk about how things move through angles, we can use theta to represent an angle. And so the set of points that we're going to get out of these functions, or of these individual functions for x and y, so I guess I shouldn't say functions, I should probably say relations. They may or may not define y as a function of x. So they might fail the vertical line test, but they are a relation. Okay? So just a quick reminder about parametric functions. And so we'll get into example 1. So in example 1, we have to sketch the parametric curve and eliminate the parameter to find an equation that relates x and y directly. Okay. So we have a few different. We've got A, B, and C to do for this. And so for part A, we have to do x is cosine t and y is sine t over the interval from 0 to 2 pi. Okay, so we said, let's see, x is cosine t and y is sine t, and we're on the interval from 0 to 2 pi. The reason why we're including 0 in our interval and we're not including 2 pi is because if you include 2 pi, you land at the point that you started at again. And so if we don't want to hit the same point twice, we don't include it. So, well, we know to eliminate these parameters, we can use the trigonometric, the Pythagorean trigonometric identity and relate these functions. So we can start off by squaring each function. So x squared is the same thing as cosine squared t, and y squared is the same thing as sine squared t. So all I did was just square everything. So if we add them together, cosine squared t plus sine squared t, we know from our Pythagorean identities that that equals 1. Okay? So then, well, if we know that cosine squared is the same thing as x squared, then we can replace that with x squared. And then for sine squared, we know that's the same thing as y squared. So then we can replace that with y squared. And so we get x squared plus y squared equals 1. And if you don't recognize this from pre-calc, this is the relation, because it's not a function, for the graph of a unit circle, right? And so a unit circle is just the circle. Its center is at the origin 0, 0, and it has a radius of 1. Right, so this point up here, this point would be 0, 1. This point here would be 1, 0. This would be 0, -1. And this would be -1, 0. Okay, so it's a circle centered at the origin with a radius of 1. And so what we have to do for example 1 is we have to sketch the parametric curve. Okay, so that would be our sketch right here. You don't have to include all of these points that I did. Just 1 is fine. We can tell that it's a circle, and so 1 should tell us that our radius is 1. And then eliminate the parameter. Well, eliminating the parameter is what we did right here. So eliminating the parameter is getting our t out. And then and that's also finding an equation that relates them. And now, so this, they didn't ask you about this, but we'll just make a note of this. This graph does not pass the vertical line test, so just an extra aside, an extra note. This parametric relation does not define y as a function of x. Okay, so the reason why it does not define y as a function of x is because it's not a function, it's a relation. It fails the vertical line test. If you wanted to define y as a function of x, you could restrict it so you're only doing the top half, the top semicircle, or just the bottom semicircle, and then in that case that would pass the vertical line test, and that would be a function. Alright, so that was 1a. So let's go on to 1b. So for this one, we have x is 3 cosine t, and y is 2 sine t, and this is going to be on the interval from 0 to 4 pi. Okay, So again, we can go ahead and square things. So we could say x squared is 9 cosine squared t, and y squared is 4 sine squared t. So then, well, if we want to get our cosine squared and our sine squared by itself, we could divide both sides by 9 here. So then I would have x squared over 9 is cosine squared t. And then on the right side, I could divide both sides by 4, and I would get y squared over 4 is sine squared t. So then, again, we could say, well, we know cosine squared t plus sine squared t is 1, using our Pythagorean identity. So then instead of writing cosine squared, we could throw in the x squared over 9, and instead of writing sine squared, we could put in the y squared over 4, and the whole thing is equal to 1. So the graph of this is going to give us an ellipse with horizontal radius of 3, a vertical radius of 2, and because we're going from 0 to 4 pi, it's actually going to be traced twice, right? Because if we were going from 0 to 2 pi, we would only go around the ellipse once, and then 4 pi, we're going around it twice. So we're going to be traced twice, and then, oh, I made a mistake. If we look at the original problem, they include it from 0 to 4 pi, and they include 4 pi in our interval. So what that means is we're actually going to land at the point 3, 0 3 times. So this is a little tricky to show in a graph. All we can do is really write it, but it does, if we were actually talking about the motion of a particle, this would be relevant, okay? So if we go ahead and get our graph going, we have a horizontal radius of 3, so that's going to be 3. That'll be -3. We have a vertical radius of 2, so that can be 2, and that can be -2. And if we draw this in, okay, and so it's going to be tracing it twice. So let's see, we would start here, and we would go that way, and we go once around, and then we go twice around, and we end up landing here 3 times. So these details, the direction, they didn't actually ask you to show, and there's no way that you can show in this particular problem that you traced it twice. They didn't ask you about that information. That's just kind of an aside that we gave just for conversational purposes and learning purposes. But this ellipse, what you would have to have for the answer to this problem is showing this ellipse right here. And then again, this fails the vertical line test, so the other thing that we could say about this is it does not define y as a function of x because it fails the vertical line test. Okay, and then this right here, this would be our relation where we eliminated the parameter. So moving on to example 1c. Okay, so for example 1c, we have x is the square root of t, y is t minus 2 for some t in the interval from 0 to 4. Okay, so if we work with this x equals the square root of t and we square both sides, we could say x squared is t. So now we have something that we could plug in for t. So then we could go to this function right here of y, and we could say, well, t is the same thing as x squared. So then we could say that y is x squared minus 2. So all I've done is take this t and take this x squared and plug it in for the t. Now, you recognize this as a quadratic equation in the graph of a parabola. So let's set up a chart and figure out what our points are going to look like. They want us to do this from 0 to 4. So we would have the points 0, 1, 2, 3, 4. I'm sorry, not the points, but the value of t. And we're going to use those to find our x values, and then also to find our y values. And we'll get some points and plot them and see what direction we go in, and how much of a portion of a parabola we have. Okay, so let's see, if we take the square root of everything, I'll have 0, 1, root 2, root 3, and 2. And then if we take our t values and plug them into this function right here, t minus 2, we're going to get -2, -1, 0, 1, and 2. Okay, so if we go ahead and plot these points, let's see, let's give ourselves a very basic graph. So first off, we'll have the point 0, -2, and then 1, -1, and then root 2, 0. Well, let's see, we know root 2 is about 1.4, so that'll be about here. And then 3, root 3. Well, none of this has to be to scale. Let's see, 3, root 3. The square root of 3 is something like 1.6 or 7. So we could approximate it, or so wait, root 3, 1, that could be somewhere in this vicinity. And then the last point, 2, 2, so we've got our 2 and then 2 out here. And so these are the t values that we had from the interval, just going from 0 to 4. And so we can see if we plot these values, what we actually get is the right half of a parabola. Okay, and we can see that this would pass the vertical line test, so we can say this does define y as a function of x. Okay, so for your answer, you need this graph, and then you need this function right there to show that we eliminated the parameter. And that's the end of example 1. Alright, and so then you can see the next slide shows these graphs done out really nicely with a nice scale and perfect shapes. So that's what we did get, so that's good. So the next thing that we want to talk about is the slope and concavity of parametric curves. And so what this is now is we're bringing the calculus into parametrics. Okay, so we can analyze the slope and concavity of parametric curves using the first and second derivatives in the same way that we did with explicitly defined curves. When I'm talking about explicitly defined curves, an example of this would be something as y is a function of x, or f of x equals x squared plus 2x minus 5, right? So the same processes that we did on those, we can do on our parametric curves. So there's just one small little difference when we go to take our derivative. The slope of a parametric curve is still going to be dy over dx, but the concavity, and the concavity is still going to be determined by our second derivative, d squared y over dx squared. But we want to be sure we understand how we're getting these first and second derivatives. When we find these first and second derivatives, instead of differentiating with respect to x, we're going to be differentiating with respect to t. And so what we're going to have to do is take the derivative of our given relation separately. So this is what we have. If x and y are both differentiable functions of t, and if we know our derivative of x with respect to t is not 0, then the the derivative dy dx of the whole parametric function is going to be dy dt over dx dt. So you take the derivatives of your function of x with respect to t and your function of y with respect to t separately, and then you divide one by the other. Now, if y prime, if our first derivative is dy dx, is also a differentiable function of t. So if you do all this work and you get something that's differentiable with respect to t, then you can find your second derivative. And so your second derivative, so this is the one that's not as intuitive. So your second derivative is going to be dy prime over dt over dx dt. So what you do, excuse me, is you take your first derivative that you got and then you put that over your x. Okay, so that's the one little piece that some students have trouble with. I think a lot of students would think, well, why don't we just take the derivative of dy dt again and put that over dx dt, take the second derivative of dx dt and put those over each other. It doesn't, because what you're doing is you're taking the derivative with respect to x the whole time, and so that's why your denominator stays the same and your denominator is still dx dt. Okay, so we can use this and move into example 2. So for example 2, they say, consider the curve that's defined parametrically by x is t squared minus 5 and y is 2 sine t on our interval from 0 to pi. So we want to sketch the graph of the curve, indicate the direction that it's being traced, and then find the highest point on the graph, and then justify our answer. And we also want to find all inflection points on the curve. Okay? Now, so we have the graph in front of us, but what we can do is we can verify some of those points. All right. So this is example 2. Okay. So the functions that were given, we have x is t squared minus 5 and y is 2 sine t, and we're on the interval from 0 to pi inclusively. Okay, so how we could kind of check some points is we could set up a table, and if I'm going from 0 to pi, well, I'll do 0, I'll do pi over 4, I'll check pi over 2, I'll check 3 pi over 4, and then I'll check pi. Okay? And so remember, x is going to be t squared minus 5, and then y is going to be 2 sine t. Okay, so we're just going to take these values and plug them into the functions that we were given. So for some of these, we'll approximate with decimals just to make things easier to graph. So if I plug pi over 4 into x, I'll get negative 4.38. Plugging pi over 2 in will give me negative 2.53. Plugging 3 pi over 4 in, that's going to be 0.55. And then plugging pi in, we're going to get 4.87. So now I can take these same values for t and plug them into 2 sine t. So I'll get 0. Let's see, plugging pi over 4 in, that's going to give me root 2, which is just 1.41. Plugging pi over 2 in, that'll give me 2. Plugging 3 pi over 4 in, that'll be root 2 again, which is 1.41, and then plugging pi in will just be 0, right? And so then, well, all of these points are already plotted for us, and so you can see how we would put these points on this graph on our x-axis running horizontally and then our y-axis. The important thing to note, the whole reason why we run through this exercise is to get this initial point, knowing that we're starting over here at negative 5, 0, and then we're ending over here at 4.87, 0. So now the way that this graph is shaped, there's only kind of one way to go from one point to the next, and there's really only one direction that you can go. It's not like some of the circles or ellipses where we could start anywhere and go in either direction and still end back at our initial point. So this is pretty clear to see, right, that we're going in that direction from the left to the right. Okay, so what you would have to do to finish part A off is just plot these points and sketch the graph, and then they want you to indicate the direction that it's traced, so then you should throw that arrow in there to show that you're going that way.